In this video, we're going to track changes that happen to different equilibrium systems when different types of stresses are added to them to see what the effect is of that stress and to see what the shift will be and how we adjust essentially to counteract that stress according to Le Chatelier's principle. So we'll do a few examples. The first one we'll start off with is changes to molarity. In other words, changing concentration. So we're going to be changing concentration here by adding or removing some reactant or some product. So here's our system at the very beginning. We have the reactants put into a vessel, and they'll react and they'll produce some product. But initially, because there's no product, the concentration of the product is 0. And initially, you have more reactant than product. You only have reactant essentially. So your reactants might start off at the same level if you have the same concentration of both. But just for the purpose of this, I'm going to put the reactants at different levels so we can follow both lines. So let's just say we have our reactants over here for H2 and a reactant over here for I2. And so what we're going to see happen is over time, our I2 will be used up, or our I2 will be used up, and so will our H2 because they're reacting to produce HI. So we're going to see a downward trend there. Then eventually, let's retry that. We're going to see a downward trend, and then eventually it stops changing when we flatline. And we're going to see the same thing for the I2 because it's being used up. We'll see it flatline as well, much like the H2. And as H2 and I2 are being used up, well, HI is being produced. So we're going to see that increase. And then it'll flatline. So at the point where they essentially flatline, and I didn't really draw this as accurately as I could have, but the point where the concentration stop changing, that's where equilibrium has been reached and will be maintained. And this is just a rough sketch. I didn't do any calculations to see when equilibrium will be reached. It's just a rough sketch. So this here again was the product being formed. Now, what I want you to get as well is that there is a reason why I made this hill for the product a little bit larger than the hill for the reactants. You'll notice that we have a 1 and 1 coefficient there. So really, this will be consumed by 1, and this will be consumed by 1 as well. Almost like the minus x, for example. Whereas here, we have a change of 2, like plus 2x. So this is like saying minus 1x, and this is like saying plus 2x like in our ICE tables. So all we've done so far is we've just tried to show when equilibrium is being established, when the concentrations of each no longer change. And so now what we're going to do is we're going to add a stress to this system. We're going to go in and we're going to throw in some H2. So let's go and add some H2 to this system. And so remember, we've added H2. So now our goal at this point is going to be to reduce the H2 that we've added. Now, to show this at the onset, what we need to do is show our sharp increase in H2 because we've added H2. So we have to show a sharp increase for H2 only. Now, since we've added H2, our goal is to reduce the amount of H2. So to do that, we need to use it up, which means that we need to shift to the right side. So to undo this stress, we need to shift left to right. So we need to use up the H2 and the I2, and that'll produce more HI. So we'll go ahead and do that. We'll get until it stops changing. And then the same thing will happen here. This will drop until it stops changing. And then this one over here will be produced because we're going towards the right, so until that stops changing. So again, this is about a change of minus 1x. This is a change of minus 1x as a coefficient. And this over here is a change of plus 2x because of the coefficient of 2. So let's try another one. Let's do a different stress this time. Let's, instead of adding some reactant, let's remove some product. Let's remove some HI. So how do we undo this? Well, to undo, we want to produce more HI because we've removed some. So to undo, we're going to shift from left to right. Now, before we do that though, we have to show that we've removed HI. So there's going to be a sharp decrease in HI, okay? But we're shifting from left to right to make some more of it now. So that means that we're going to have to use up some more of the H2, and we're going to have to use up some more of the I2 as well because we are making some more HI. So we're going to use this up. We're going to use this up. My drop should have been probably a bit more significant because it's a bit inconsistent with what I did before, but this again is a minus 1x. This is a minus 1x. And then this one here, because I'm producing some HI, so initially we had a sharp decrease. This will go up. Plus 2x. And again, until it flatlines. So essentially every time I have my shift, I do reestablish equilibrium again, right? When it stops changing, when the concentration of everything stops changing, I've reestablished equilibrium because the rate of the forward and reverse are the same. So you won't have a change in the concentrations anymore. So once we say a flat line, we've established a new equilibrium every time after our stress has happened. So these green parts are all equilibria, where equilibrium has been established, and they all have the same K. So when you change the concentration of a reactant or product by either adding or removing, you do cause a shift, and they will end up at different concentrations. But when you take the ratio using your K equilibrium expression, you're going to get the same K value again. So these all have the same K. So you should be able to sketch or graph a situation like this where you can show equilibrium being established. If I tell you a certain stress was added at a certain time, can you show what's happening, especially when it comes to concentration, and show how the system will adjust itself and what changes will occur, and do understand that they all have the same K value when we're dealing with molarity changes. So in this video, our focus is molarity changes. In the next video, we're going to take a look at temperature changes and do a similar exercise, but instead with temperature changes.